Good day, stat students. So today we're going to go over section 10.1, and let's say that CNN does some sort of poll to determine the approval rating for Barack Obama. So we'll go back a couple of presidents, right? And so now we know this, is that instead of asking all Americans if they approve of President Obama's, uh, job, what he's doing in his with regards to the presidency, uh, meaning we're not going to take a census, right? We're not going to take a census. We're unwilling to do that. So what are we going to do? We're going to take a look at 1,015 adult Americans and hopefully do it as randomly as possible. Here was the results: is that President Obama had a 47% approval rating with a margin of error of 3%. And so what they would do, meaning the media, they would put 47% in big bold numbers on the TV or on your computer screen. All right. But then if you looked in the margins, okay, you look in the very side of the screen or the very bottom of the screen, what they'll say is that there was a margin of error of plus or minus 3%, or they might just say plus or minus 3% somewhere. So what exactly does that mean? And so here's our conclusion: is that our sample showed the approval rating for President Obama was 47%, but that was for the sample. That was for the sample. I can't stress that enough. That was for the sample. But it is possible that the true percentage could be 3% higher or 3% lower than this result. So in other words, it could be as low as 44%, the approval rating, or as high as what? 50%. So what exactly happened then? Well, the president has a 47% approval rating with a margin of 3%. And the only way to actually know this, I'm just kind of reviewing here, the only way to actually know this is that the population portion B is to conduct a census, and we're willing to do that. So we took a random sample instead. And what did we calculate? What did CNN calculate? They calculated what? P hat. They calculated P hat. And they calculated out to be what? 47%. So that's P hat, the sample proportion. And then we apply the margin of error to the P hat. So we get 47% plus or minus the 3%. And so our best estimate of the population portion P, the approval rating for all US adults, is somewhere between 44%, 50%, and what we're going to call this is a confidence interval. So a confidence interval is when we come up with a set of values that we think are plausible values for some sort of parameter, in this case the population portion P. And we're going to designate the confidence interval with a CI, so we don't have to keep on writing it over and over and over again. All right, so that's what we're going to study here in general, is confidence intervals in this section. So please do not skip this. Many students do. Is that the generalized formula for a confidence interval is the following: point estimate plus or minus the margin of error. And we just saw that with our example. All right. So let's focus in on the margin of error. All right. I'm sorry. Please do not skip. Please do not skip this following formula here. So every confidence interval has a very generalized formula. It is the point estimate plus or minus the margin of error. All right. Please do not skip over that. And what we're going to focus in is right now is the point estimate. So what is a point estimate? A point estimate is a single number that is the value of a sample statistic such as p hat or x bar. And so you can see our example here. Here was p hat, and we went out a certain distance here to estimate the population portion P. Now, these next 2 points are very important. It'll make your lives so much easier. So if creating a confidence interval for the population portion of P, then P hat is the point estimate. However, if creating a confidence interval for mu, then X bar is the point estimate. Then X bar is the point estimate. All right. Please do not skip over that. So what I'm trying to tell you is that the point estimate isn't always P hat. It just depends on if we're creating a confidence interval for mu, population portion P, or for some other parameter. All right. That means the value that the statistic that we're going to start with is probably going to be different than, say, P hat or X bar or whatever. Okay. It just depends on the parameter that we're estimating. All right, so let's think about the margin of error a little bit. The margin of error, what is it? The margin of error accounts for what's called sampling error. Sampling error is a kind of a bad term, along with, say, the margin of error, because error sounds like a mistake was made. No mistake was made. Actually, sampling error just happens by chance, right? And what is sampling error? Sampling error is the difference between a parameter and its corresponding statistic. And so it just sort of happens by chance, right? So here's an example. We take a random sample of 1,000 UA students and ask, do you work during the year? All right. So what we found out from the last section that we studied, the last chapter, we do not expect our p-hat, okay, the percentage of the 1,000 UA students from the sample that work, we don't expect that to equal what? The percentage of all UA students that work. We don't expect those two percentages to equal to one another. However, what did we find out though? That these values should be reasonably close to one another. All right. So this is a graph that we looked at in 9.4. Okay, and this is representing the sampling distribution of p-hats. So these are all the different p-hats that you could possibly get of a certain sample size. All right, and what did we find out was the center of this thing? Well, whatever the value of p is, that's the number that's going to be right there. So we know that the value of p is going to be in the center of the sampling distribution for p-hat. And let's take a look at this stuff here. It says here about 68% of all the samples will be within what? One standard deviation of 0.512. 95% of all the p-hats are going to be within what? 2 standard deviations of the center, and about 99.7% of all the p-hats are going to be within 3 standard deviations of the center. Okay? And so we expect our p-hat to be close to what? The center of the sampling distribution. Okay? And so here's the idea here, is that maybe our p-hat was located, could have been located here, could have been located over here. Let's say it was located here. And so what we're doing with the confidence interval is that we're starting with p-hat. We're going to go out a couple of standard deviations this way, a couple of standard deviations this way. And we're going to say that we're pretty sure that the population portion p is located between here and here. And notice that we captured 0.512 in that confidence interval. And that's the idea here, right? That's the whole idea. So the margin of error can be broken down into 2 pieces parts. The margin of error can be broken down into what's called the critical value times the standard error. All right. So the margin of error is the critical value times the standard error. And I want to focus in on the standard error right now. All right. Standard error is a modification of the standard deviation of the sampling distribution. Simple as that. So recall that the standard deviation of p-hat is the following. But there's an obvious problem using this formula for this section, meaning creating a confidence interval for the population portion p. There's an obvious problem here. Okay, maybe pause the video and try to think this one through. Why can't we use this, all right, to create a confidence interval for the population portion p? Hopefully it's, if you think about it, it's kind of obvious. Well, the whole reason for creating the confidence interval for a parameter is because you don't know that value. So here we don't know the value of the population portion p. So how can we use it in a formula to go find itself? It doesn't make any sense, right? So here's a solution. So if we can't use the population proportion, we use this sample proportion in its place and call the formula something else. Okay. So here's the standard deviation of the sampling distribution of p-hat, but we can't use p in this formula, so we get rid of it. Okay. And we're going to replace it with p-hat and call it something else. Okay. And so the standard error of the sampling distribution of p-hat is just a slight, it's a slight modification of this up here, and it's just substituting p-hat in for p. And so this is the standard error. That's what's going to be the last part of the confidence interval. How about a confidence interval for the population mean mu? All right, let's think about this. From the last section, we learned that this is equal to sigma divided by the square root of n. So in the last chapter, we found that out. All right. Now, there's a problem using this formula to create a confidence interval for mu. All right. This one's a little bit tougher to figure out, but if you think about it long enough, you should be able to figure it out. All right. So here's the answer here. Okay. What is sigma? Sigma is the standard deviation of the x's, of all the x's. So maybe a good thing I should have put here all the x's. Okay. So in order to know this formula, you need to know all the values of x. All right. And if you know all the values of x, we should be able to calculate mu. Mu is the population mean. So if you know all the values of x, you should be able to calculate the population mean mu. All right. So the reason we want to create a confidence interval for mu is because we're willing to collect all the values for x. Take a census, right? And so that's why we're creating a confidence interval for mu. All right. So in other words, if you don't know sigma, you don't know mu. That also means if you don't know mu, you don't know sigma. All right. So that's the logic there. All right. And if you don't know the population standard deviation, we use the sample standard deviation instead and call it something else. So, all right. So in this formula here, we don't know sigma, so that goes away. What are we going to replace it with? We're going to replace it with the sample standard deviation, S. We're going to call this formula something slightly different. We're going to call it the standard error. All right. So there's the standard error of the sampling distribution x bar. Sample standard deviation, S divided by the square root of n. That's the last part of the formula for the confidence interval for mu. All right, there's your standard error. All right, let's concentrate now on the critical value. So the critical value is the number of standard errors to go out in both directions to create the confidence interval. The text, by the way, if you decide to read the text closely, the text calls this the multiplier, and this is the only textbook I've ever seen it being called the multiplier. I've always seen it being called the critical value. So if you want to use the idea of multiplier, that's fine. I know, obviously, I heard of the term before, all right? But I'm going to call it the critical value because I think that would serve a good purpose here. I think you're going to hear critical value a heck of a lot more than multiplier, all right? This value comes from probability distribution such as the standard normal, okay, like Z, okay, or some other probability distribution, and depends upon what we call the confidence level. Confidence level is the probability that our process will produce a confidence interval that will contain the parameter. All right, so the confidence level is the probability that our process, that the overall process will produce a confidence interval that will contain the parameter. We're going to kind of stress this later on, that idea, kind of planting the seed. We'll see it again, okay, if you didn't quite get it. All right, we're gonna bring up that idea again. All right. So if creating a confidence interval for the population portion P, okay, so hint, this does not apply when creating a confidence interval for mu. All right. If the confidence level is stated at 95%, as you can imagine, because of the empirical rule, our critical value should be right around 2. Remember, we said it was about 95%, about 95% of the data is within 2. Okay, well, you can change that around. 95% is about 2 standard deviations, or in this case, standard errors away. And so you can imagine where that 1.96 came from. Okay, we're just being more precise than the empirical rule. Okay, now there are other confidence levels that you can use other than 95%. And so, so where did I get this idea from? Again, it's from right here. I was just trying to stress that with this slide here. Okay. Now you can use other confidence levels, like you can use 90%, and the critical value in that case would be 1.645. Then I've also seen 98, 99. 98 would be 2.33, 99 would be 2.58, and again, this is just when creating a confidence interval for the population portion P. It's all based upon the standard normal table, okay? And so you can use that table for the test, okay? And when you do your homework, use these values right here. That should be good enough, okay? You don't have to be too much more precise than that. All right, how about a critical value for a confidence interval for mu? All right, so remember our standard error was this. So we are using S, the sample standard deviation of the formula. Oh, so unfortunately this creates another problem, okay? This is a little bit harder to think through because this took actually several decades for mathematicians and statisticians to figure this out. Why does using S create a problem? All right. Well, it is a statistic, and every statistic varies from sample to sample. It is not a single value like sigma. All right. So S is a statistic. It varies from sample to sample. Okay. And so it's moving around. Just depends on what people or what things you brought into the sample, right? Therefore, by using S, we have more uncertainty built in the formula, and we have to account for this extra uncertainty. All right, we have to account for this extra uncertainty, and so the solution is that actually this is kind of interesting. A guy who worked at Guinness Brewery in Ireland figured this out, and so so what we do is we use what's called the t-distribution of the set instead of the standard normal, and the critical value is going to be just slightly bigger than it would have been if using z. All right, so we're going to use the t-distribution, when working with mu. All right, so I got out of PowerPoint and I'm showing you the t-table now. And so the t-table is really easy to understand. There's a couple of things that we need to understand about it. First of all, is that here are the different critical levels. Okay, so you got 80, that's pretty low, but you got your typical ones here, 90, 95, 98, 99. You got this 99.8, whatever. Okay, but mainly the middle four is going to be used. Okay, and you got this DF over here, and it stands for degrees of freedom. And the easiest way to understand degrees of freedom is that every time you got to estimate a parameter within a formula, all right, you lose a piece of information in order to do that, okay? And so what happens then when you create a confidence interval for mu, okay? When you create a confidence interval for mu, remember, we couldn't use sigma in the formula, right? We couldn't use sigma. And so we had to estimate that parameter. And so what happens then is that we lose basically one piece of information, okay? And that's what degrees of freedom kind of stands for, all right? And so I don't want to go into any more details than that, okay? But when you create a confidence interval for mu, okay, simply speaking, is that the degrees of freedom is equal to n minus 1. We had to estimate one parameter, and so the amount of information that we have is n. We lost one piece of information because of estimating one parameter. And so simply the degrees of freedom is equal to n minus 1 when you're creating a confidence interval for mu, okay? So for instance, let's say that you had 11 for a sample size. That means our degrees of freedom is 10. Let's say that we're creating a 95% confidence interval. Then we would put a critical value down for t as 2.228. Simple as that. A 99% confidence interval, let's say that we're creating, and our sample size was 17. That means our degrees of freedom would be 16. So we would have a critical value of 2.921. Simple as that. The last thing I want to show you with regards to the t-table is that notice as the degrees of freedom goes up, what's happening to the critical value. So it started at 12.7, and then it's all the way down to 2.101 when you get to 18 degrees of freedom. So as degrees of freedom goes up, the critical values start to go down, right? Starts to go down. And so notice where it eventually converges at infinity. These values sound familiar to you? 1.645, 1.96, 2.33, if you round to two decimal places, 2.58. Yeah, they're the values of z. Okay, so as the degrees of freedom goes up and all the way up to infinity, the t is equal to the standard normal. They converge. And if you were a statistics major, you would show this theoretically, right? Here, all I want you to know is that you don't really have to create your own little table. You can just have this table handy, the t-table, and say, okay, if I'm creating a confidence interval for P, the values for Z are right here, okay? Right down here where degrees of freedom is in infinity, because T converges to the Z at that many degrees of freedom. For any other degrees of freedom, okay, for any other degrees of freedom, okay, you would have to use a t-table, okay? And for the most part, when you do your homework, you're probably going to be able to find the critical values off this table. Now, in the course, if you look, I have also given you an Excel spreadsheet that has a lot more degrees of freedom than this. So if you just happen to run into a homework problem that is not on this table, please check out the Excel spreadsheet that I've also provided to you in the course. All right, and open that one up. Just check it out and check out the degrees of freedom that you want, and the critical value will be given to you there. All right, so t-table. Okay. All right. So the critical value, like I said, oh, this was supposed to, hold on. I see that this guy right here should be mu. I didn't change it over to a symbol. So the critical value that when we're creating a confidence interval for mu, we use the symbol t with a little cv instead of z because we're using the t distribution. Okay. So again, you have to figure out the critical values from the t-table, and the degrees of freedom is equal to n minus 1. Again, that is only when you're making a confidence interval for mu. Okay. All right, so let's review. So if the variable we collect the data for is categorical, and we want to create a confidence interval for the population portion P, the formula is the following. All right, so you got P hat plus or minus the critical value that's coming from the standard normal, and then you got your standard error. And we're going to study this more closely in section 10.2 part 1. And if we're creating a confidence interval for mu, here's the formula. So point estimate would be x bar plus or minus the critical values coming from the t-table, degrees of freedom at n minus 1, and then there's your standard error times, so you got your standard error s divided by the square root of n. So these guys right here are being multiplied, and just like over here, this is being multiplied by the standard error, okay? So formula for confidence interval for P, formula for the confidence interval for mu, all right? And we're going to study this guy right here when we get to chapter 11, okay? Thank you for your time today.